On this section 2.1, we're going to be covering the basics of functions and their graphs. Now, the first thing we're going to go through is a couple of definitions, concepts that you need to know from this section. First of all is a relation. Now, a relation is any set of ordered pairs. When we mention the word set, a set means nothing else but a collection or a list. Ordered pairs means points. So when we say a set of ordered pairs, means it is a collection or a list of points. That's what makes a relation. Now, the collection of all the x components of the relation is going to be called the domain. Okay. Then the collection of all the y components is going to be called the range. Okay. So now we're going to cover one more concept, which is the definition of a function. Now, a function is a correspondence from a first set called the domain to a second set in which each element in the domain corresponds to exactly one element of the range. That means that every value of x must have exactly one y. Okay? But in order for it to be a function, only every value of x must have one y, but every value of y does not necessarily need to have one x. Okay? In other words, the value of x cannot be repeated, but the value of y can be repeated in order for a relation to become a function. Now let's go ahead and take a look to this example. It says determine whether the relation is a function, then give the domain and range of the relation. Now, looking at this relation right here, we can automatically see that the value of x, every value of x has more than one y. So x equals 5 has two different values of y. 5 has two values of y, mainly 3 and 4. That means that if the x is being repeated, right, for two different values of y. Likewise, the 8 has two different values of y, which is 3 and 4. So that means automatically that this one will not be a function because every value of x does not have only one y. It has two y's. So we're going to say this relation, the relation does not represent a function. Now the domain and the range would basically be all the collection of all the x values will be the domain of this relation. So all the x values will be just 5 and 8 because those are the only two x values on this relation. So even though the 5 is being repeated, we're just gonna write it one time. Now likewise, the range of this relation is gonna be the values 3 and 4. Those are the only values of y of this relation. So these values represent the range. And they're being repeated, so we just write the range, each value we just write it once. Okay. Now let's take a look to the next definition. Now how do we determine that an equation is actually a function? This is what we're going to get into. If an equation is solved for y and more than one value of y can be obtained for a given x, then the equation does not represent a function. Once again, this is telling you that you need to solve an equation for y, and then you need to create kind of like a table for different values of x to determine if any value of x has more than one y. Okay, so that way we can determine if it's not a function. If every value of x gives me only one y, when I create a little table, then that means that the given relation, the given equation represents a function. Otherwise, it's not. Alright, so let's take a look to the first example here. Then I'm going to give you kind of an idea, a better idea of what makes a function in terms of an equation. So we got x squared plus y equals 169. So if we solve this equation for y, all I gotta do is subtract the x squared from both sides. That's gonna give me y equals negative x squared plus 169. So let's say, for example, that we want to create a little table for this. This is basically what the method we are going to use to graph functions later on today. So let's say give any value of x. For example, let's start with, let's say, negative 2. So just a single value. So if I substitute it into the equation to find the value of y, then this is what we're going to get. Negative and then x, which is negative 2 squared plus 169. And then check that out. What is that going to give me? Negative 2 squared, it's going to be 4. Times a negative, it's a negative 4. Plus 169 is 165. So what do you see? That when x is equal to negative 2, y is equal to 165. And that's the only value. So this value of x has only one y. Now let's think about another value. Let's say 0, for example. If I substitute a 0 into the x right here, 0 squared is going to be 0 times a negative, it's still 0, plus 169, it's going to be 169. So what do you notice here? When x is equal to 0, y is 169. And you can see that that's the only value of y for this value of x. Now let's try another one. What if x is 1? Negative and then 1 squared plus 169 equals 1 squared is 1 times a negative, it's going to give me a negative 1 plus 169 is 168. So when x is equal to 1, y is 168. So what you're 168. So what you're looking at right here is that no matter what value of x we pick, the value of y is going to be unique. So meaning that for every value of x, there will be exactly only one y. So what does that tell us? That we can continue with the table, but this tells us that yes, y is a function of x in this equation. Yes, y is a function of x. When I say y is a function of x, that means that it is a function. That's what we're basically saying. Then I'm going to give you a better idea of how to remember, basically, when we see these types of equations, an easier way to determine if they are functions or not. Okay? Now, let's take a look to the next question. Now, let's go ahead and do the same thing in this problem. On this one, we're going to use a little concept from remedial mathematics, which is the square root property that we're going to have to use here. So if I want to leave the y by itself, what I need to do is move the x squared over to the other side. That's going to give me y squared equals negative x squared plus 9. But in this case, that's not the only thing. Now, we need to also get rid of this square right here on the equation. And based on what we cover in section P3, we covered that a couple of sections ago. Remember that, remember about the square root, okay? The square root basically represents the same thing as a power of 1/2. So if I would raise the y squared to the power of 1/2, remember the product rule tells me that I need to multiply them. What happens if I multiply 2 times a 1/2? That's going to give me a 1. So, but what does the power of 1/2 mean? The square root. So basically another way of writing this out, it would be this. So that 1/2 means the square root of y squared. So that means that whenever we have the square root and a square, they simplify each other. The square root and the square, they're opposite operations. Okay? So that's what we have to do here. In order for me to get rid of the square on this equation, I need to take the square root on both sides of this equation. But this is called the square root property. The square root property tells you that anytime I do the square root, the solution can be plus or minus. Like for example, the square root of 16, it can be positive 4 or negative 4, because 4 times 4 is 16, but also negative 4 times negative 4 is 16. So whenever we take the square root on both sides of an equation, in the solution is going to be a plus or minus in front of the square root, positive or negative. Now I want you to try this. What happens now if I pick any value of x? Let's start with the simple one. What if I choose 0? Substitute it. So y is going to be plus or minus the square root of negative 0 squared plus 9. 0 squared is going to be 0 plus 9, it's going to be 9. And if I put plus or minus the square root of 9, that is going to be plus or minus 3. What does that mean? That when, I'm going to write it right here, that when x is equal to 0, y is equal to 3, but also when x is equal to 0, y is equal to negative 3. Now, I can try it with any other value. Let's say, for example, what if we try it with, let me think about one. Let's say, let me think about one. I want to think about one that doesn't give me a negative right here. So what if we try, well, let's just try the positive one. Yeah, it doesn't matter. So what if we put that? Square root of negative and then 1 squared plus 9. That is going to give me plus or minus the square root of negative, 1 squared is going to be 1 times a negative is negative 1 plus 9, it's going to give me an 8. So then you can simplify it and everything, but based on what I showed you on P3, but I'm not going to simplify it. All I need to tell you is this, that when x is equal to 1, y is equal to the square root of 8, and when x is equal to 1, y is also equal to the negative square root of 8. That's what the plus or minus means. So what do we notice in this type of examples? That every value of x has two different values of y. So when x is 0, y is 3, but also it can be negative 3. When x is 1, y is equal to the square root of 8, but it can also be the negative square root of 8. And that would happen for all of the values of x. Okay? So that automatically tells us that since that one repeats, the value of x repeats in this function, I mean on this equation, that means that no, y is not a function of x. It is not a function. Now, I want you to look at this equation and make a comparison with the previous equation on the previous problem. What is the difference in this equation that makes the, this not to be a function compared to the previous equation? This equation has a y squared. Now, that tells us the following. Anytime, not only for y squared, but anytime I have an equation, and this is a good thing for you to remember, anytime I have an equation in which the y is being raised to an even power, not only 2, but if it's also raised to the 4th or to the 6th or to the 8th power, anytime the y is being raised to an even power, that function or that that equation will automatically not be a function, because this is going to happen if we create a table for those type of situations. So once again, anytime we have an equation in which the y is being raised to an even power, that automatically will tell you that that equation does not represent a function. This is just an idea. But ultimately, this is how we check everything. We have to leave the y by itself, and then we create a table of values for any given x, and see if for any given x we get two different values of y. If we don't, if we only get one single value of y, like I did here, for every x that I substituted, I got only one y. Then it is a function in that case. If you get more than one y for any given x, then it's not a function. That's what the definition right here tells you. Now, that's for equations. Now, how do we determine that a graph, this is for graphs, how do we determine that a graph represents a function or not? Very simple. To notice or to determine if any value of x is being repeated by looking at a graph, all we have to do is what is called the vertical line test. That tells you the following, that I just draw a vertical line on the equation, on the graph, I'm sorry. If any vertical line that I draw intersects my graph in more than one point, then that is an indication that that given graph is not a function. When a vertical line intersects the graph more than once, that tells you that that specific value of x on that vertical line has two different values of y or more. If any vertical line intersects the graph at more than one point, that means that any value of x, that specific value of x, has two y's or more y's, depending on how many times that vertical line intersects the graph. Okay, so that's how we determine that if a graph represents a function or not. Let's go ahead and take a look to the next problem. I have several graphs, but I just picked one for you on this lecture. We're going to use the vertical line test to identify graphs in which y is a function of x. So we're just going to take a look at this one. Using the vertical line test, can we say that this graph represents a function or not a function? It does represent a function, because if I draw a vertical line, let's say here, how many times is the graph being intersected? Only once. If I draw a vertical line here, how many times is the graph being intersected? Only once. No matter where I draw a vertical line, if I draw it on the right side, right here, how many times has it been intersected? Only once. What does that tell me? That every value of x is only intersected at one y, meaning that each value of x contains only one value of y. And that is the definition of a function. So we're going to say that yes, the graph shown represents y as a function of x, or represents a function. Now we're going to get into the function notation. Now once we know that an equation represents a function, then we're going to transcribe it. We're going to write it in a different way using what is called function notation. So for example, one of the equations that we had right here before, for example this one, y equals negative x squared plus 169. We knew that that one was a function. So what we can do is this. Since y equals negative x squared plus 169 was a function, then we say that this one was a yes, right? It was a function. So what does that mean? We can rewrite it using function notation. The y can be transcribed using the notation f of x. That means the function f with respect to the variable x. Now we don't have to call it function f. It can be called differently. We can also call it g of x, or we can call it h of x. We can call it t of x. This is just the name of the function. Okay? But remember that that notation f of x, g of x, or h of x represents the value of the y. Okay? So the y can be represented in many different ways using just a letter to give the name to the function. So that fx means the function f with respect to the variable x, meaning that it is a function called f that contains the variable x in it. This one is a function called function g containing the variable x in it, and so on and so on and so on. So once again, the f of x, g of x, h of x, or t of x represents the value of the function, which in other words, the value of the function means the value of y at any number x. That's what it tells you right here. Alright, so now we're going to evaluate some functions in this using the function notation. So we're going to go ahead and do this problem here. Evaluate the function f of x equals x squared minus 5x minus 2 at the given values of the independent variable and simplify. Now when we say the independent variable means at the given values of x. So the first thing we're going to find out in this function is we're going to find f of 2. Means that we want to find the y value when x is equal to 2. That's what the f of 2 means. Find the y value. Anytime we want to find f of x, that means the value of y at any given x. So once again, find the y value when x is 2. So we're going to replace the 2 into every x of this equation. It would be x, which is 2 to the second power, minus 5 times x, which is 2, minus 2. That's this equation right here. And then we're going to simplify it. So 2 squared is going to be 4, minus 5 times 2 is going to be 10, minus 2. Then if we combine like all the values, all the like terms, 4 minus 10 is negative 6, minus 2, it's negative 8. So when x is negative 2, y is equal, when x is 2, y is equal to negative 8. That's what this tells us. Okay. Now, the next situation. Now we want to find out this function value, f of x plus 9. That means that we want to find the value of y when x is being replaced with an x plus 9. So we need to replace both of these x's with this expression, x plus 9. So instead of x squared, we're going to put x plus 9 squared. Instead of minus 5 times x, it's going to be minus 5 times x plus 9, and then minus 2. Every x here was replaced with the x plus 9. And then we have to simplify it. Now, what does it mean by the x plus 9 squared? Then that means that we need to multiply x plus 9 times x plus 9. Or you can do the binomial square, just the formula that I show you. The square of the first term plus 2 times the first times the second term plus the square of the second term. You can square it that way, or if it makes it simpler, you can just write it 2 times. X plus 9 times x plus 9, and then multiply it 2 times itself. Okay, so we're going to distribute all of it to find the result for this, and that is going to give us, let's distribute, x times x is going to be x squared, x times 9, it's going to be plus 9x. Then we're given this, which is 9 times x is going to be plus 9x, and then 9 times 9 is going to be plus 81. Now we have to do the same thing here. Negative 5 times x is minus 5x, and negative 5 times 9 is minus 45. And then of course we have the minus 2 right here on the side. What else can we do to simplify this? We can combine like terms. So the x squared is going to go alone. Then what we can combine is the 9x plus the 9x minus the 5x to begin with. So 9x plus 9x is 18x, minus 5x is plus 13x. Then we can also combine the 81 minus 45 minus 2. So 81 minus 45 is 36, minus 2 is 34. So that would be a plus 34. And this is the solution for this one. What does this mean? That when x is equal to x plus 9, y is equal to x squared plus 13x plus 34. That's the meaning of this expression. Last but not least, now we need to find letter C, f of negative x. What does it mean by f of negative x? It means that we want to find the value of y when x is replaced with a negative x. So we're going to go to the equation right here, and we're going to replace both of these x's with a negative x. So instead of x squared, it's going to be a negative x squared. Instead of minus 5 times x, it's going to be minus 5 times negative x, and then the minus 2. Then we're going to simplify this. Now keep in mind this. When I square a negative, it's always going to become a positive. Anytime I raise a negative to an even power, it is always going to result into a positive. Negative x times negative x is positive x squared. Negative 5 times negative x is positive 5x, and then minus 2. And this is the solution for this. We cannot combine any like terms. So what does this mean? That when x is equal to negative x, y is equal to x squared plus 5x minus 2. These kind of operations that we're doing right here, this is the main ones that we're going to use in this section. But these ones, the B and the C, we're going to use those kinds of operations in a later section. Basically, we're going to see them in section 2.2. This one in 2.2 in an application about the negative x, you're going to see that. And also in section 3.4. And this one, we're going to see this type of operations in section 2.6. Okay. Alright, so now let's work on the graphing part of the section. So we're going to graph the given functions f and g in the same rectangular coordinate system, and then we're going to describe how the graph of g is related to the graph of f. So we're going to begin by graphing the function f of x. The way we graph a function usually is going to be the following way. We need to create a table of values for x and f of x, just like I showed you when we were determining if an equation represents a function. That's exactly what we have to do to graph a function, create a table of values for at any given values of x. And my suggestions when you create a table is for you to use the following values: -2, -1, 0, +1, and +2. However, just keep in mind that in order for me to graph a function, at the most you are required to have 3 points. Okay, with the exception of this function that I'm looking at here, because I'm going to show you what this one consists of. This is going to be what we call a linear function. Whenever we have a linear function, that's the only exception. This one, we actually only need 2 points when graphing it. At least 2. Now that doesn't mean that I strictly have to get 2 points, but the minimum number of points that I need for a linear function is going to be 2. So we're going to replace, in order for me to find the value of y, we're going to replace each one of these values of x that we selected into this equation. So we're going to have -4 times x, which is -2. That's going to equal to 8. This one, -4 times x, which is -1. That is equal to 4. This one, -4 times x, which is 0. That gives us a 0. Next one, -4 times x, which is 1. That gives us a -4. And the last one, -4 times x, which is 2. That gives us a -8. Okay, so let's go ahead and graph this equation or this function. Now, what makes it a function based on the definition? Why is it that we say automatically that this one is a function? Well, first of all, because they already put it in the notation of f of x. That means that it is a function. But not only that, we can also say that it is a function because by creating a table, what do you notice? That every value of x that we pick gives you a different value of y. Okay, so gives you one value of y only. So every value of x gives you only one value of y. So the same value of x, it doesn't have multiple values of y, just like we had on one of the previous equations. So let's go ahead and graph this. So this means that when x is equal to -2, y is equal to 8. When x is equal to -1, y is equal to 4. When x is equal to 0, y is 0. When x is equal to 1, y is -4. And when x is equal to 2, y is -8. So when we plot these points, it's -2, -8 is down here. Then we have -1, -2 and 8. It goes up the +8. So -2 and +8 is here. Then -1 and +4. Then the next one, 0, 0. The next one, 1, -4. And the next one, 2, -8. So that will create what we call a linear function. Remember I mentioned to you that anytime we have a function, how do we recognize it to be linear? If we have a function that has x raised to the first power and of course y raised to the first power. Okay, but if we have a function in which x is being raised to the first power, that creates a linear function, which is a line. Now we're going to create the graph of g of x. So we're basically going to do the exact same thing. So for g of x, we're going to create another table. So g of x, you see what it gives you? -4x minus 3. So I'm going to do the same values, -2, -1, 0, 1, and +2. What do we notice right here on this equation compared to this one that we just did? Well, we already have the -4x is exactly what we did right here. and these are the values that we got for negative 4x. So then what do we have to do additionally that this equation tells you? You have to do a minus 3. So basically that minus 3 is going to be affecting these values right here, because that's where the minus 3 is being subtracted, right? So what are these values in these points right here? The y's, right? So what does that mean? That any time that I have a function that looks exactly the same thing as another function, same equation, the only difference is that one function has a plus a number or minus a number. That number is going to affect the y's in the sense that it's going to be either added or subtracted to the y values. In this case, we already know that if I substitute it, for example, if I substitute the negative 2 again right here, and then we do the minus 3, negative 4 times negative 2 gives you 8, but then minus 3, that's going to give you 5. Wouldn't it be the same thing as if I just do a minus 3 right here? That will still give me that 5, right? So that will give you the point negative 2, comma 5. So all we have to do, we don't have to recreate the table. Since anytime we have two functions that have the same equation, the only difference is a minus a constant or plus a constant, that constant is going to be added or subtracted to the y values. So I'm just going to do that. If I subtract 4 minus 3, that's going to give me a 1 right here. 0 minus 3 is negative 3. Then if I do negative 4 minus 3 is negative 7. Then if I do negative 8 minus 3 is negative 11. So you see the points for g of x are going to be this. Negative 2, 5, and then negative 1, comma 1. Then we have 0, comma negative 3. Then we have 1, comma negative 7. And then we have 2, comma negative 11. So let's graph those points. Negative 2, comma 5. So it's going to intersect it right here. The next one. Negative 1, comma 1. It's going to intersect it right here. The next one, 0, comma, negative 3, right here. 1, comma, negative 7. Negative 7 is right here. And then 2, comma, negative 11. Negative 11 is going to be right here. So you see that there's two parallel lines that we're going to get. If we graph the g of x, it's going to be parallel to the other one, to f of x. That's basically what we're going to have. Let me just make it more accurate here. This is what we are going to see on the function g of x. Okay, so we need to describe or find a relationship between f of x and g of x, and all I want you to look at is look at the points, these points that we originally had. What happened from this point to this point right here? This point was shifted 3 units lower. Now what happened from this point to this point right here? That point was shifted 3 units lower. So if we continue, we can actually identify that each one of these points, to get from one point to the next point, those points were shifted 3 units lower. So that tells us this constant that we have on the side, that minus 3, is going to cause the graph to shift up or down depending on the sign. And it is always going to happen with any graph, and it will always affect the y values. So we're going to describe the following right here. We're going to say that the graph of g of x, I'm just going to make a description of how the graphs are related. The graph of g of x is the graph of f of x, but shifted 3 units down. Okay. That's exactly the difference between this function f of x and g of x. It is that g of x, it is a function that was shifted down 3 units. Now, I'm going to give you another idea when it comes to lines. When it comes to lines, there is another way that we can graph them. So I'm going to spend a little bit more time on the lines. Okay. So the tables is usually the general way of graphing any equation. So we're going to keep using this for the rest of the functions. -2, -1, 0, 1, and 2. However, when it comes to a linear function, we can also graph it in a different way. So I'm going to show that here. So we know that the functions were f of x equals -4x, and we have g of x equals -4x minus 3. So this one, you see that it doesn't have a constant. So if it doesn't have a constant, that means it is a 0 as a constant. Okay? So let me bring down my graph right here, because we're going to be using another graph. I'm going to do something else here, separate. So let me move this to the side. So another way that we can use to graph lines, just specifically for lines, okay? This method that we're going to learn right now is just for lines, okay? We can use what is called the slope and the y-intercept of the line, okay? So that is anytime we need to make sure that the equation is in the form y equals mx plus b. So it has to be this in this form, and this is called the slope-intercept form. Why is it called the slope-intercept form? It is because if I write the equation in this form, the constant that you have on the side right here, it is going to represent the y-intercept of the graph. So what does it mean by the y-intercept? It means that it intersects the y-axis at that location. So that 0 means that this graph touches the y-axis right here in the middle at 0. And then this number on the side, that one is called the slope. The slope is -4, but it needs to be a fraction. So if it's not a fraction, you need to put it over 1. And what does the slope tell me? The slope tells me basically the number of units that the graph is increasing or decreasing to get from one point to the next point. We call it the change in y over the change in x, or some people call it rise over run. So this number on the numerator, -4, means that the y value, it is changing by -4, meaning that it is decreasing or going down 4 units. And this 1, this is my run or my change in x, which means that if it is the x is increasing by 1, meaning that it's going to the right 1 unit. So from the 0 that we have right here, this graph is going to keep shifting 4 units down and to the right 1 unit to get from one point to the next. So 1, 2, 3, 4 units down and to the right 1 unit. Here should be another point. Then you can do it again. 1, 2, 3, 4 units down and then to the right 1 unit. Here should be another point. Then the next one. 1, 2, 3, 4, and 1 to the right. Here should be another point. And so on and so on and so on. If you compare those points to the line in black, those points should be the exact same points as the line in black that we created. Okay, so this is my function f of x, as you can see. So, to get the function g of x, we're going to do the exact same process. So we already know that in this equation, this -3, it is the y-intercept. So that means that this line crosses the y-axis at -3. That's what the y-intercept means. And this -4, it is called the slope. And that slope, again, it is a -4, meaning it is -4 over 1. And a -4/1 means that the graph is going down 4 units and to the right 1 unit. So once again, from this point it goes 1, 2, 3, 4 down and then to the right 1 unit. Here is another point on the graph. Then it's going to go 1, 2, 3, 4 down and then to the right 1 unit, and then it keeps on going 1, 2, 3, 4 down and then to the right 1 unit. And if you compare those points to the points that we obtain in g of x, they should be the exact same points. They don't change. Okay? So the most efficient way to graph a line, it would be best that if you follow this process with the slope and the y-intercept other than the table. So you will still get the same thing. Okay? Let's go through the next graph. Now for the rest of the graphs, we're going to use the table method. Only for lines, we can use this other methodology, which is the slope and the y-intercept, to create its graph. Let's get to the next one here. Now we're going to be graphing these two functions f and g in the same rectangular coordinate system and describe how the graph of g is related to the graph of f. Okay, so let's go ahead and start with f of x as usual. So to create the graph of f of x, we need to construct a table of values. And remember, f of x equals negative x squared. On this table of values, we're going to use the same numbers: -2, -1, 0, 1, and 2. Try to stick to these numbers. These will be the best numbers you can use when creating the graph of what we call a parent function. Now, we're going to start with this: negative and then x, which is -2 to the second power. Negative and then x, which is -1 to the second. Negative and then x, which is 0 to the second. Negative and then x, which is 1 to the second. And negative x, which is 2 to the second. And then we evaluate these points. We evaluate this function. So -2 to the second power is going to be 4. But then 4 multiplied times the negative on the outside, it's going to make it a -4. -1 times -1, which is -1 squared, gives me +1. But then times the negative on the outside, it gives me a -1. 0 squared is 0. Times the negative, it's still going to give me a 0. 1 squared is going to give me a 1. Times the negative, it's a -1. And 2 squared, it's going to give me a 4. Times the negative, it's going to give me a -4. Okay, you see that every value of x has only one value of y. The values of x are not being repeated. Okay, now that means that for the function f of x, we get the points -2, -4, then -1, -1, 0, 0, 1, -1, and 2, -4. So let's graph that function. So -2, 4 is located right here. -1, 1 is here. 0, 0, then 1, 1, and 2, 4. So anytime we have a function that has x to the second power, that function is going to create the shape of what we call a parabola, or a U shape. That's what the function x squared is going to create, a U shape. Oh, but wait a minute, I think I put the points wrong, so it was the other way around. So let me fix it. So it was -2, -4. So it was -2, -4. So it was down here. -1, -1. So it was backwards. Then 0, 0. Then 1, -1. And the last one is 2, -4. Okay. So I was looking at something else. So this is going to be my parabola. So this parabola basically is the same shape, but it opens downward. It looks like a U shape, but downward. Okay. So this is going to be the graph of f of x. Now, to create the graph of g of x, we're going to do what I told you to do, which is, you see that these two functions have the exact same equation, -x squared. The only difference on g of x is that g of x has a +8. Why do we notice that plus constant, or that constant, is going to have as an effect on the graph? It is going to be added to the y values. If we recreate the table, that's what's going to happen. It is the same thing as adding this number to the y value. So instead of recreating the table again, that's all I'm going to do to make it easier. So g of x is going to consist of the points -2, +4, -1, 7, 0, 8, then 1, 7, and 2, +4. So we graph that. It's going to be -2, +4, then -1, 7, then 0, 8, then 1, 7, and then 2, 4. It is still the same shape. It is the same as the function f of x. The only difference is that this one was what happened to get from here to here. The function was shifted up 8 units from one point to the next point to the next point to the next point and to the next point. All of the points shifted up 8 units. So when we describe the relationship between them, all you're going to say is this. The graph of g of x is the graph of f of x, but shifted up 8 units, or shifted 8 units up. And this is basically the description that we need for that again. Now, so keep in mind now that anytime I have a function with x squared, it's going to have the shape of a u. Okay. Now, let's talk about the next one. We have graph the given functions f and g in the same rectangular coordinate system. Describe how the graph of g is related to the graph of f. Now, this one is going to be called the absolute value function. You see, f of x is equal to the absolute value of x, and g of x equals to the absolute value of x plus 5. So we're going to do the same thing in this problem. We're going to start by creating the table for the function f of x again. So we're going to say x, and then we're going to find f of x. And f of x consists of the equation absolute value of every x that we pick. So we're going to pick the values -2, -1, 0, 1, and 2. So if I substitute them into this equation, it will be the absolute value of x, which is -2, absolute value of -1, absolute value of 0, absolute value of 1, and absolute value of 2. Now, let's talk about the following. What is the absolute value means? It means the distance from 0 to that number -2. And when we talk about distance, distance means it is a positive number. So the best thing to say here is anytime we take the absolute value of a number, it is just going to make it a positive. Just like distance. Distance is a positive number. So the absolute value of -2 is +2. Absolute value of -1 is +1. Absolute value of 0 is just 0. That one is already positive, so it's going to stay the same. And absolute value of 2, that's already positive, so it stays the same. So, for the function f of x, we got the points -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2. And let's go ahead and graph this function. So, the graph of this function is going to look like -2, +2. It is up here. -1, +1. 0, 0, 1, 1, and 2, 2. So now keep this in mind. Anytime we have an absolute value function, when we graph it, it's going to look like a V shape. That's what that function is basically going to look. Okay, so any absolute value function is going to look like a V shape. So this is a function f of x. Now, based on what we see, once again, you see that they have the exact same equations, right? G of x has the exact equation. The only difference for g of x is the +5. And remember what that +5 is going to do? It is going to be added to the y values. So we're going to have a +5 on all of the y's right here. So +5 to this y, +5 to this y, +5, and +5. That's going to give me the points -2, 7, -1, 6, then 0, 5, then 1, 6, and 2, 7. So -2, 7, it is going to be up here, -1, 6, 0, 5, 1, 6, and 2, 7. It is the exact same graph, but shifted 5 units up. That's how we're going to describe this. Okay, this is a graph of G. So we're going to describe the relationship of these two graphs by saying the following, that the graph of g of x is the graph of f of x but shifted 5 units up, and that is my description. Now we're gonna get to the next one. On the next graph, we're gonna graph this function f of x equals x to the third power and g of x equals to x to the third power plus 4. So we're gonna follow the same strategy. So we're gonna first create the table for f of x and f of x equals to x to the third power. So we're gonna start with, again, same values: -2, -1, 0, 1, and +2. So this one is going to be -2. X cubed means -2 to the third power, so we're going to cube these values. These are my x's. -1 to the third power, 0 to the third power, and then 1 to the third power, and then the last one is 2 to the third power. So -2 to the third power means -2 times -2 times -2, which is -8. -1 to the third power means -1 times -1 times -1, and that is -1. 0 to the third power is going to be 0. 1 to the third power is 1, and 2 to the third power is +8. So the function f of x gives us the points -2, comma, -8, -1, comma, -1, 0, comma, 0, 1, comma, 1, and 2, comma, 8. So when we graph this, it's gonna look like this. So -2, comma, -8 is down here. -1, -1, 0, 0, 1, 1, and 2, comma, 8. So the graph of f of x equals to x cubed. It is always going to have the following shape. It is basically called, it has like a nickname. It's called a snake. This is basically the shape of x to the third power. Okay, so this is a graph of f of x. Now we're gonna do the exact same thing for g of x, but now you see that g of x, the only difference is that it has a +4. So just like I showed you, we don't have to basically recreate the table. That +4 is going to be added to the y values from the f of x originally. So that is going to give us the following points. So my function g of x is going to contain the points -2, comma, -8 plus 4 is -4. -1, comma, -1 plus 4 is a 3. 0, comma, 0 plus 4 is 4. 1, comma, 1 plus 4 is a 5. And 2, comma, 8 plus 4 is going to be a 12. So let's graph those points. -2, comma, -4, it is down here. -1, comma, 3, it is up here. 0, 4, it is here. 1, 5, it is here. And the last one is going to be 2, comma, and 12. It is going to be here. So when we connect them, it's going to create the exact same shape. But the only difference is that this one was shifted up 4 units. Every point was shifted up 4 units. So that's what we're going to explain right here when we describe the relationship between the two graphs. We're going to say that the graph of g of x is the graph of f of x, but shifted 4 units up. And this is the description. Okay, We have three more graphs that we're going to do. The next one. Graph the given functions f and g in the same rectangular coordinate system and describe how the graph of g is related to the graph of x. F of x equals to 5 and g of x equals -1. On this function right here, just giving you a little idea, we don't really need to create a table, and let me show you why. Okay, let's say for example that I want to create the table for f of x. F of x equals 5. So what if I put, let's say, -2, -1, 0, 1, and 2 for this? Where am I supposed to substitute these values of x if there is no x on this equation? We cannot substitute them anywhere. What does it mean by f of x equals 5? That means that it doesn't matter what value of x you pick, the value of y is always going to be a 5. And what is it going to look like if I graph these points? For example, -2, 5, -1, 5, 0, 5, 1, 5, 2, 5. So what do we see there? We see that this graph, it is going to generate a horizontal line through the y equals 5. So in fact, this is what I want you to keep in mind. Anytime I have a function in the form y equals to a number, or y is the same thing as f of x, y equals to a number, or f of x equals to a number, which is the exact same thing, that is always going to generate a horizontal line. We don't need to create a table for that one. Okay. Now we're going to do the exact same thing here. G of x equals -1, so this is f of x. Let me put a little note here. G of x equals -1 would be a horizontal line through the -1 down here on the y-axis. So we're going to have a horizontal line at this location. That's what that one is going to be. And that's g of x. So we're going to describe the relationship between them. So we're going to say that the graph of g of x is the graph of f of x, but what happened to get from here to here? It was shifted down 1, 2, 3, 4, 5, 6 units. So we're going to say but shifted 6 units down. That's the relationship between these two graphs. The next one. We're going to talk about this one now. Graph the given functions f and g in the same rectangular coordinate system. This graph that we're going to do right here, it is going to be the only exception to the rule of what we have done so far. This is going to be the only exception to the rule. And the reason is this. Because if I want to create a table, remember that we just covered the sections about radicals. Okay, section P.3 and section 1.4. Now, if I just tell you, you don't, like for example, if I want to pick the values, -2, -1, 0, 1, and 2, what's going to happen if I substitute it? What is the square root of -2 equals to? It is a non-real solution, because nothing squared can give me -2. What is the square root of -1 equals to? It is a non-real solution, once again, because nothing squared equals -1. Now, what is the square root of 0? That one is 0. That one is okay. You see? What is the square root of 1? 1 squared equals 1, so that one equals 1. So that one is okay. But what is the square root of 2? That one is going to be 1.41, and so on and so on. So you see that there are some values out of these in the list that we picked that do not work, and some of them that do. First of all, the square root, we cannot have a negative inside of the square root. That is for sure. That is a rule. Okay? So negatives are out. The only values that do work is these 0 and 1. But what do we know about 0 and 1? That both of those numbers are perfect squares. So when you are graphing the square roots, what you need to do is you need to pick perfect squares. And in this problem, they give you the values, the perfect squares that you must use, of course. 0, that was the first one that we saw it work. 1, the next perfect square is 4, and the next perfect square is 9. Those are the values that we can use here. 0, 1, 4, and 9. So when I do the square root of 0, that one is equal to 0. The square root of 1, that one is 1. The square root of 4, that one is going to be 2. And the square root of 9, that one is going to be 3. So for the function f of x, we get the point 0, 0, 1, 1, 4, 2, and 9, 3. So if I want to create the sketch of this function, what do we need to do? Well, let's plot those points. First one, 0, 0 is going to be through the origin. Then 1, 1, it is right here. Then 4, 2, it is right here. And then 9, 3, it is right here. So if we connect those points, it has this shape. It is basically like half of a U shape but going sideways. That's what the square root looks like. Half of a U shape going sideways. We call that the eyebrow. Okay, so the eyebrow. So this function has the shape of an eyebrow. Okay. Now, the next thing that we're going to do, remember that these two functions, f and g, are the same equation, square root of x and square root of x. The only difference is that g of x has a plus 5, meaning that all of the y values will be added 5 units. So if I add 5 units to all of the y values, then this is going to give me the point for g of x, which is going to be 0, 5, 1, 6, 4, 7, and 9, 8. So let's graph those. 0, 5, then 1, 6, then 4, 7, and the last one is 9, and 8. And then we connect these points, and this is going to be the graph of g of x. So what do we see is the difference? That all of the points right here were shifted up 5 units. That's what we're going to describe as the relationship between the two graphs. So we're going to say that the graph of g of x is the graph of f of x, but shifted 5 units up. And that is the relationship between the two graphs. And the last graph that we're going to create, this last one, it is not a function. You're going to see why. Graph the following equation in the rectangular coordinate system. Now, for this type of equation, you see that this equation doesn't have any y. It just tells you that x is equal to 7. What does that mean? That means that it doesn't matter what value of y we pick. It doesn't matter what y is. X is always going to give me a value of 7, because x is always equals to 7 in this equation. So that means if we got, for example, 7, -2, so it is right here. 7, -1, 7, 0, 7, 1, 7, 2. So anytime I have an equation in the form of x equals to a number, what does it make? It makes a vertical line. But this is not, you see that it says equation, it doesn't say function, because we know by the definition of function that a vertical line is not a function. Because if I do the vertical line test on this vertical line, it's going to intersect the line many times. So this is not a function. You see that the same value of x has too many values of y, so it's being repeated. So this is just an equation, it is just a relation. Okay, so keep in mind that anytime we have an equation in the form x equals to a number c, that is going to generate a vertical line through that number c. Now, this concludes the graph. Now we're going to go over a couple of more items in this section, a couple of definitions that we need to do. Basically, how do we find the domain and range of a function if I show you the graph of it? Now, to find the domain and range given any graph, all we got to do when you're looking at a graph, you need to include or count all of the values of x that have a point in any given graph. Now, if I want to find the range, likewise, given a graph, all I have to do is you need to include all of the values of y that have a point on that graph. So that's basically how we determine the domain and the range from a given graph. So on the next example, I'm going to basically show you how it's going to be done. Okay. Now, one more thing, and these are we already have one definition here that I talked to you about, which is the y-intercept. The y-intercept is the point where the graph crosses the y-axis. So to find the y-intercept, you look at where the graph of whatever function crosses the y-axis. Now, to find the x-intercepts, the x-intercepts will be the points for which the graph crosses the x-axis. Okay, that's how we find them. Now, on the other hand, keep in mind this statement right here, which is a very important fact. A function can have more than one x-intercept, but at the most one y-intercept. Because if I have a function that has more than one y-intercept, then it is not a function because of the vertical line test. Okay, so this is what I'm talking about. If we have, let's say, a function with one y-intercept here and another one here, the vertical line test fails, because if I do a vertical line, then you will see that the line intersects the graph at 2 points. Okay, so that tells you that the same value of x has two different values of y. So keep in mind that for any function, there is only one y-intercept at the most, and it can have one x-intercept or more. There is no limit on the number of x-intercepts in a function. So we're going to analyze the next function right here, which is this one. Use the graph to determine letter A, the function's domain, letter B, the function's range, letter C, the x-intercept, if any, letter D, the y-intercept, if any, and letter E, the missing values f of -2 and f of +2. So, first thing that we're going to find in this function is the domain and the range. So, for the domain and the range, this is what I want you to keep in mind. What I mentioned to you is that the domain represents all of the values of x that have a point on the graph. So let me just give you a few examples. Like, for example, x equals to 1 have a point on the graph. X equals to -1 has a point on the graph. X equals to 0 has a point on the graph. X equals to 1 has a point on the graph. X equals to 2, x equals to 3, x equals to 4. And those are not the only ones, because this graph is we call it a continuous graph, meaning that it's connected, it keeps on going. So also we can say that -0.5 has a point right here on the graph, -0.5. We can also say that +0.5 has a point on the graph, 1.5 has a point on the graph, 0.1, 0.2, 0.3, and so on and so on and so on. Now, we cannot make a list of every single value of x that belongs to this graph. It is going to be impossible because it contains infinitely many of them. So, just keep in mind, this graph keeps on going this way, right? The arrow tells us that it keeps on going this way, and it keeps on going this way. That means that -2 is not the smallest value of x on the graph. -3 is also right here on the bottom on the graph. -4, we will also be able to find it all the way down here on the graph. So -5, -20, -100. So any negative value will exist on this graph. Also, if the graph doesn't stop here at the number 4. The 5 also has a point right here on the graph. 6 also has a point on the bottom. 7, 10, 20, 30, and so on and so on. Because the graph keeps on going both to the left side and to the right side. So this is what you are going to do. To give the domain when there's infinitely many values, we're going to use, we can still write it in set notation, but we're going to write it like this. The set of all x such that. This is how you read this. The set of all x such that, and to say that x can be any negative number or any positive number, all we have to say is that x is any real number. That's how we give the domain in set notation when there's an infinite set of values. Okay. Now, something that I do want to mention, when you give the domain and the range in the set notation, the only symbols that you can use for the set notation is, of course, one of them is any real number, another one is less than, greater than, less than or equal, greater than or equal, or not equal to. I just want you to keep that in mind. These are the symbols that we use when we're given the domain in the set notation when there's an infinite set of values in the domain, or range. So, the next thing, I'm going to show you another way in which we can express the domain when there's infinitely many values. The other way is called the interval notation. So for the interval notation, there are only two things that we need. We're going to put it in parentheses or brackets. Parentheses means that the initial value, or the what is called this value right here on the endpoint and this endpoint are not included. The square bracket means that the endpoints are included. Okay, so in this case, what we have to give for the interval notation, we have to give the smallest value, comma, and the largest value. And this means that the domain would go from this number, comma, all the way to this number. That's another way of writing my domain in interval notation. The interval tells you it's a specific range of values from here to here. That's what we're saying. So in this particular problem, since the domain consists of all the negatives and all the positives, because all the negative values are on the graph and all the positive values are on the graph, then we can say that the domain is any number from negative infinity, comma, all the way to positive infinity. Not included. We put parentheses because we cannot include infinities. Infinities means that it just keeps on going. It cannot be included. Now, we are going to do the same thing for the range. Now, what do we know about the graph on the bottom? The graph on the bottom keeps going down. So it keeps going down on this side and on this side. So that means that -5 is not the smallest value of y. So it's not -6, it is not -7, it is not -8, it is not -9. There is no smallest value. It keeps on going all the way down to negative infinity. So that's what we know about this graph. And now the highest value that we can find on the graph right here on the y-axis is going to be the number 4. But what do you notice on the number 4? That it is included because it has a point. The graph of this function has a point at this 4. So that means when you write it in interval notation, you're going to say that the range is any number from the smallest value, which is negative infinity. This is my smallest y value in the graph, comma, all the way to the highest value of y, which is positive 4, and it is included, so we're going to put a square bracket at the 4. Now, we can also write it in set notation. But in set notation, it's not going to be x, since the range is going to be the set of all y such that. Okay? And in order for me to say that y is any number from negative infinity to 4, you see that it is anything below 4. Remember that for the set notation, you can use the symbols right here. If I want to say that the range consists of any value of x that is below the number 4 or equal to 4, we can use the symbol, less than or equal to 4. So we can say that the range is the set of all y such that y is a number less than or equal to 4. And that is the range in both notations, either the set notation or the interval notation. Letter C. Now we are going to find the x-intercepts. Now the x-intercepts refer to the points where the graph crosses the x-axis. So this graph crosses the x-axis at -1 and at +3. So my x-intercepts are x equals to -1, comma, and +3. The next one. Now letter D. For letter D, we're going to find the y-intercept. What does it mean by the y-intercept? The point where the graph crosses the y-axis. So this graph crosses the y-axis right here at y equals to 3. Or we can also say the point 0, 3. Also for the x-intercept, we can say x equals to -1 and 3, or we can say the points -1, 0 and 3, 0. Okay, so we can say it in either way. Okay. Last but not least, we have two more things to find in this function right here. We need to find f of -2 and f of +2. This is the last question. What does it mean by f of -2 or f of +2? That means that we're trying to find the y value when x is equal to -2 and the y value when x is equal to +2. So all we gotta do is this. For f of -2, go to the graph at when x is -2. When x is -2 means right here. And go to the graph. The graph is located down here on the bottom. All you gotta do is find the point at x equals to -2. Here it is. And all we gotta do is find the y value. What is the y value at this point right here? The y value is -5. So f of -2 equals -5. Likewise, now we're going to find the y value when x is 2. So we go to the +2 right here. We just need to locate the point on the graph at +2, which is going to be up here. And the y value at this point right here is going to be a 3. So that means f of 2 equals to 3, which means that when x is equal to 2, y is equal to a 3. And this problem concludes the section 2.1, which is Introduction to Functions.